Yeah, I mean, I thought I finished yesterday most of the stuff, and there were a few slides left, and but I think we actually addressed some of those slides with your good questions. But because today we had a bit of extra time, JP mentioned that maybe we can cover the rest of the slides. But I would say, feel free to interrupt, and we could just have a conversation instead of me just kind of lecturing you. But okay, so we went through the cellular method, we went through the augmented plane waves, and I will cover these orthogonal plane waves. I may talk a bit about the pseudopotential, but I actually don't have slides on it. Okay, so in the orthogonal plane wave method is an alternative approach, again, to combine the rapid oscillations in the core region with the plane wave-like behavior in the interstitial region. However, we did the same thing in the augmented plane wave approach, but we did it by assuming a muffin tin potential, a potential that has an atomic structure within the muffin tin radius, and it goes to 0 in the interstitials. That was the approach that would use the APW, the augmented plane wave. But the OPW, which is the orthogonal plane wave, it does not require the muffin tin structure. So that's sort of an advantage of this method. Okay, so we don't need the muffin tin potential. And the reason for it is that in the orthogonal plane wave method, we actually separate the two wave functions. We have a psi of v for the valence wave function, and we have a psi of c for the core wave functions. Whereas in the augmented plane wave, the entire wave function, it was one wave function really. But in the orthogonal plane wave, we separate out into two wave functions. Again, the C, or the core wave function, it consists of atomic orbitals. They're well localized in some region that is close to the nucleus. And then you have the valence wave function that is constructed from superposition of this kind of structure. So you have two parts to it. These are called the orthogonal plane waves. You have two parts to it. The first part is e to the ik dot r, plus the second part is some wave function that is constructed from the core wave functions with some coefficient. So in the augmented plane wave, we had one wave function that was made of an atomic-like structure modulated by a plane wave. But here we don't have that modulation. We actually have two different sectors of this wave function. It's a plane wave plus an atomic-like wave function. So that's the difference. And here, in order to play the game, you have to determine these B coefficients. You have to find out these B coefficients properly to write down the orthogonal plane waves. Okay, now let me see what I have here. So you can essentially, this is restating the same thing. You simply have a few of these core wave functions with a proper coefficient, and you sum it with a plane wave, and you make your orthogonal plane waves. Okay, the advantage, another advantage of this method is that it sort of shows very nicely how your valence bands are directly orthogonal to your core electrons. So we're going to see here, in fact, in this slide. So here is the orthogonal plane wave made of a plane wave and a series of functions that are core-like times some coefficient. And then you want to determine these coefficients. In order to determine them, you require an orthogonality condition. So the integral of core wave function star times orthogonal plane wave should be 0. So say psi 1 star, psi 2, the integral should be 0, whereas the first wave function are the core wave functions. The second wave function is this orthogonal, the orthogonal plane waves. And if you plug in this function simply into phi, you will come up with a B. If you just simply plug this wave function into this formula, what you're going to get is two terms. The first term is a multiplication of e to the I k dot r times psi c star, that part survives. That's what you see here. The second part is psi k itself, psi k of c times psi k c of star. That part will disappear because these wave functions themselves, they are an orthonormal set. So for any c, let's say for any c prime other than c, you will get a delta function, and it just goes to 0. So what you end up with is that these b coefficients are simply given by an integral with a minus sign, because you just have to plug this in here, of the core atomic-like wave function times plane waves. So that's how you calculate these b coefficients inside this orthogonal plane wave. So by construct, so right here you can see that by construct, this wave function is made so that it is automatically orthogonal to the core bands. So if you have core bands, for example, you have some kind of oscillatory pattern near the nucleus. That's where the electrons that are close to the nucleus, they have a higher kinetic energy, so you have a more like oscillatory pattern here. Your valence band, they also have some oscillatory pattern near the nuclei, but the oscillatory pattern of the valence bands are orthogonal to the oscillatory pattern of the core bands. And this way, you really separated out the two wave functions, the valence wave functions from the core wave functions. And that's actually the reason why you do not have to have a muffin tin potential here. You can have any potential you want and you can do your calculation. Okay, and the other thing, the second sort of automatic advantage of this method is that this integral, although there is no limit to this integral, you can evaluate the integral within every unit cell. It so happens that the main contribution to this integral is only within the core region, roughly speaking. Here the core region is not well defined really, but because the core wave functions themselves, they start to exponentially decay as you get away from the nuclei. The contribution that you get for each of these coefficients is almost nothing when you get away from the core region in every unit cell. Okay, so automatically all these oscillations of the orthogonal plane waves, they're automatically bounded within a region that's very close to the nuclei. And the rest of the wave function becomes a plane wave function, which is the second part right here. It becomes the e to the ik dot r. So now, in order to construct the actual, the complete wave function that is the solution to your lattice Schrodinger equation, you need to evaluate all these b coefficients, these bc coefficients, and you have to evaluate your orthogonal plane waves, and then you have to sum over all the reciprocal lattice sites. And again, this part has the same problems as you had in the augmented plane wave. This sum can have a large number of terms, or you usually don't sum over infinite number of terms. You always terminate it at some point. This is again has the same issue as you had with augmented plane wave. There is this parameter called the RK max, which tells you what is the maximum k value that you cut this sum over k, the capital K, which is the reciprocal zone, the reciprocal lattice vector. And usually you do this over maybe, 20 or 30 wave functions, and you stop at some point. And based on how many of these terms you include in your sum, you will have some accuracy to your calculation. Again, the bottom line over here is that all the DFT calculation, they have to be cut at some point, and therefore they're all approximately correct. They're not always absolutely correct. Now that you construct this orthogonal plane wave by finding the coefficient, by making it automatically orthogonal to the core levels, that's why they are called orthogonal plane wave. You calculate the psi wave function after truncating this sum at some k max value. Then you plug this wave function into a functional for energy, as we discussed yesterday. This part is similar to the augmented plane wave. You calculate the functional, and you write down the functional in terms of psi. It has a kinetic energy, and it has a potential energy, and then you demand this functional to be stationary with respect to psi. So the dE d psi has to go to 0, which gives you a set of equations as say C, depending on how many of C's you have here in your wave function. So you will get, for example, if you have, say, 12 terms in the sum, you will get 12 equations, and you have to sort of diagonalize a 12 by 12 matrix to get the solutions that are your band structure. You get the energies here that are your band structure. Yes, you had a question.
So for this orthogonal plane wave method, so you don't care about the connection between your valence band wave function and your core wave function.
Yeah.
Like the wave function does not have to be continuous.
That's right. Yes, that's right. They don't have to. So this is, in some sense, it's a bit more relaxed than the augmented plane wave. In the augmented plane wave, you had to care about these issues. But here, what you have is that you simply separate. You have two separate sets of wave functions. You have the core wave functions, that are the atomic wave functions. You set up your orthogonal plane waves that are made of a plane wave plus a part where this part, which you demand this part to be orthogonal to your core wave functions, and then you get from here, you get your coefficients, right? And so that gives you the wave, that gives you your total wave function.
That's up with the assumption, then I understand it, but does it mean that you could have some singularity?
You can. Yes, it's true. Yes, it's a subtle point. That's right. You have to have this boundary condition always. So as you approach the core region, you always want your wave function to be continuous. And so here the wave function itself is continuous, but it so happens that the derivative of a wave function can be discontinuous. It is, in fact, a downfall of this method. And so what happens is that, for example, when you calculate things that depend on the second derivative of the wave function, the quantities may blow up, and you usually track it back to this exact problem, that where you right at the intersect between the interstitial and the core, usually the problem is that your orthogonal wave function may have a discontinuity in the slope. Yes, and that is in fact a downfall of this. That's a downfall of this point. That is why this problem does not happen when you have a muffin tin potential. It never, in fact, the muffin tin was designed to avoid such problems. And in fact, this is why the augmented plane wave and the muffin tin potential are much more frequently used than this method. So the reason why I'm showing this method is because to some extent this method shows you two things. It shows you the orthogonality of the valence band to the core bands, and the fact that the valence band have an oscillatory part that is orthogonal to the oscillatory part of the core wave functions. And the second advantage of this method is that this plane wave sector of the wave function explains why the nearly free electron approximation that we learn in our condensed matter courses, why it works so well. Because usually, in fact, this part is the largest part of the wave function, usually. But in fact, I must say that in most of modern computations, it's the augmented plane wave that's being used and not the orthogonal plane wave, for the exact same reason that you mentioned. Okay, going back again to this, the fact that why is it that the nearly free electron approach works so well, what you learn in your condensed or solid state courses. If you plug in the orthogonal plane wave in this equation, in the energy functional, of course you have a kinetic energy. That part, there's nothing very special about it. But this part that has the potential to it, this part is going to have two contributions in it. One comes from this e to the ik dot, and the other part e to the ik dot r, and the other part comes from this part, from the core wave functions. And I, in fact, talked about this yesterday, that when you plug it in this term, the e to the ik dot r term here, in fact, will be cancelled, because you will have an e to the ik dot r and e to the minus ik dot r, and they cancel each other. And therefore, the contribution of the plane wave to this term, to the potential term in your variational approach, will be negligible, will be zero. But the main contribution comes from an integral that has this form. It has a form of, say, psi. Let's say you can almost take this now to be the core wave function, so psi star times u times psi. And this integral itself becomes very small usually. And the reason why it's small is because u is, of course, your atomic potential. But phi here has this oscillatory pattern. The black is the orthogonal wave function. For the valence electron, the red is the core wave function. Both of them are oscillatory. So what happens is that you're multiplying this oscillatory wave function to some smooth potential, and then you're integrating over this. And when you integrate an oscillatory part that goes from plus to minus by some smooth potential, and you integrate over it, usually this becomes very small because of this oscillatory pattern of the phi wave functions. They the plus and minus, they don't cancel exactly each other, but they give you usually some small term. And that is why the main contribution to this energy functional, in fact, is from the kinetic energy of the plane waves. And that is why the nearly free electron approach works so well in condensed matter physics. A lot of things we do, even in cuprate physics, all these estimates that in almost every Nature and Science paper by the experts in cuprate field are done, these are all based on Druid model. This is the stuff that you learn in your, I don't know, 4th or 5th lecture in solid state 1, pretty much. All of these approximations are coming from Druid model. Druid's paper was published in 1900, exactly in 1900. And today, all of these research that we do on strongly correlated materials, you have specific heat and you want to connect it to, I don't know, some exotic physics. What you do is that you do Druid model. And it works really well. It explains a lot of things. And you ask your question, okay, why did we learn since 1900 until today? What did we learn during all this time, right? Why? The thing is that we learned a lot of things and we learned a lot of subtleties, but just the nearly free electron approach works extremely well. And now you can see why it works so extremely well. All right. So even you perfect the precision of band structure calculation, still the biggest contribution to this energy functional is from the first term, still, which is simply plane wave. Here I'm showing a band structure that's calculated with orthogonal plane waves for aluminum. And the solid lines are the results of an exact calculation, or not exact, but a DFT calculation. And the dashed lines are simply the results of a free electron approximation. So you see that these are pretty much quadratic. You see this is h bar squared k squared over 2m. And then you hit the Bragg plane, and then you open a gap, but it again continues as quadratic. And if you if you just draw the band structure from simply exactly just plane wave, just h bar squared k squared over 2m, you get the same thing. So here there is no distinction between in fact here you have the dashed lines and the solid lines on top of each other. The only difference is maybe about here, and the only difference that you see here is that the dashed lines that come from a free electron approximation, they do not distinguish or they do not appreciate a lifting of degeneracy between two bands. So here you have one band that is twofold degenerate, but when you do the actual calculation, there will be some degeneracy that's going to be lifted by the calculation. So that part, the calculation gives you something extra. It tells you, okay, these bands are not going to be exactly degenerate because you have some potential, and the two bands can separate. But other than that, a free electron calculation gives you almost exactly the correct result, which is quite remarkable. So here is an interface again for the VN2K program. It has a graphical user face, a graphical user interface that you can use. But most of the times, if you want to do the calculations, you just simply have to. So it's better usually to just use a terminal and you write your code and operate that way. But you can really, you can start with generation of a structure. You put in your lattice type. You determine your structure, say the ABC unit cells or the angles. You put all the unit cell parameters in there. You determine your atoms. You determine the Wyckoff positions. And the next thing that you would do is that you have to determine the radius of your muffin tin. And the program usually picks it as half the distance between the nearest neighbors, but you can ask the program to reduce that, and as you reduce it, the computational cost goes up, because then you're in fact you're sort of telling the program to do a little bit more work by giving it exactly some radius for the muffin tin, not just half the distance between two nearest neighbor. So the computational cost usually goes up when you do that. But yeah, so the essential approach to run the program is that you have to give it the space group, you have to give it the program will calculate for you all the symmetries of the space group. It in fact calculates for you all the symmetries of the band structure, which is very helpful for topological materials. The program will tell you one of the advantages of this program is that it will give you for example, the eigenvalues of the parity operator for every band. So then you can go ahead and, for example, look at those eigenvalues. You evaluate them at the high symmetry points in the Brillouin zone, let's say at the K point or at the M point or X point, and then you multiply these numbers for all the bands. And if the multiplication gives you a -1, you have a topological band structure. If it gives you a +1, you have a trivial band structure. This is pretty much exactly the approach that Fu and Kane and Melle introduced in order to detect the topological band structure from the trivial ones. We had a discussion yesterday a bit about the magnetism that one of you guys asked about it. So here I did not talk about the magnetic structure, magnetic calculations, but if you have magnetic calculation, then your U will have an extra term. It will have also a spin-spin, sort of a spin-spin interaction. And then you have to include the spin part of the wave functions, which I did not show at all here. So again, the computational cost goes up. You can include the spin orbit coupling in your calculation. You will ask the program to do that for you. You have to do a little bit of work so that the program doesn't confuse itself, but you can include the spin orbit coupling. All of these are really almost perturbative these are additional perturbative structures to the free electron approximation. So still your free electron approximation works really, really well. And once you do all of this, and once you do the calculation, another thing that you can calculate are the forces between the atoms. So now you have the periodic potential of the lattice. You calculated the wave function, so you know the charge distribution within the lattice. So the distribution of electric charge will modulate the forces between the nuclei. And now you can calculate the forces between the atoms, which eventually will translate into a phonon band structure. So not only you can calculate the electronic band structure, you can also calculate the phonon band structure. And so they say if you're looking at superconductivity, like the kind of thing that Weiwei does, for example, then you need to kind of look at both sides of this. You need to look at the phonon band structure, you need to look at the electronic band structure. You can calculate the density of states, and you can even calculate once you have the band structure, you can calculate some of the optical properties of the material. You can generate, for example, the X-ray spectrum, the high energy X-ray spectra from your core levels. You can look at all of these interesting and exciting parameters that you can measure experimentally. For example, if you do electron loss spectroscopy, you do EELS spectroscopy, then you can electron energy loss spectroscopy, you can calculate the spectrum of EELS, and then you can go and measure EELS, and then you can compare between your DFT and the calculated and the experimentally measured quantities. You can even calculate hyperfine interactions that you can say measure by NMR. So there's a lot that DFT can offer. In fact, you can calculate NMR spectra from these calculations. I think for the most part, I think I really covered all of this. Yeah, so yes, there was again, going back to the discussion that Jason was having yesterday about how DFT calculations give you a good handle on structural transitions. One of the things that you can do is that once you calculate the force constants, you can use the force constants to calculate, say, phonon band structure, but you can also minimize the lattice potential based on the force constants. And for, let's say, if you have two very close structures, let's say, for example, Julia was today talking about these two, the cubic versus the tetragonal the body center tetragonal structure. For the same system, you can input the two structures, and you can ask the DFT code to calculate the total energy of the lattice for each structure. I have not done this for that material, but in fact it would be very interesting. I'm pretty sure the answer would, the answer, it has to always the experimentals are always correct. The answer has to follow the experiments. You will see that they say if you do a minimization of the lattice energy, for example, for the tetragonal phase, you will get a lower total energy than for the cubic phase. So sometimes if it's difficult for you to distinguish one symmetry from the other symmetry, you can do this lattice optimizations by DFT, and it will tell you if the tetragonal phase is more stable than the cubic phase. You can also use these guidelines sometimes to sort of design new materials. These are at very, very early stages at this point, but there are efforts underway that DFT people are trying to even use this to kind of artificially make new materials. And by artificially making new materials, what it means is that they select certain elements from the periodic table, they assume a certain crystal structure, and they start calculating the lattice energy. And they see where the lattice energy minimizes, and they will tell you, oh, if you, for example, use these 3 elements and you want to make a, say, cubic system, it will become a face center and not a body center, for example. So these are the sort of ongoing efforts in the DFT community. And I want to thank everybody. I'll be here again if you want to talk more about all of this. And thank you, JP, for organizing amazing workshop.